Hi, welcome to another video. Today we are going to talk about eventual consistency. And what is eventual consistency? It's flexible consistency for scalability and availability. Let's get into it. To understand eventual consistency, we need to start from the CAP theorem. Why eventual consistency is important and it takes place. So let's do a quick recap of CAP theorem. In a distributed system, you can only achieve 2 out of the 3: consistency, availability, and partition tolerance. But the reality is the partition tolerance is almost always a necessity because network failures can happen because different components of the system is deployed across a network mesh, and it might happen that one component fails while the other component is operational. So eventual consistency choice, it prioritizes availability and partition tolerance over immediate strong consistency. And what is the trade-off? The data might be temporarily inconsistent, but the system remains operational and highly scalable. And eventually, which is the key bit here, all replicas converge. So given a period without new updates, all replicas of a data item will eventually converge to the same value. And what are the key characteristics here? Asynchronous replication. Updates propagate in the background. No immediate guarantees. A read after a write might return stale data. And eventually is relative. Time to convergence varies millisecond to hours based on system design and load. So for example, let's say in a leader-follower based architecture of a database, I send a write request to the leader, and the leader has 2 followers. So immediately after writing the data, before the data is actually replicated to the followers, I send a read request, and the read request might be directed to the follower. In that case, I can read stale data. That is one example of a drawback that eventual consistency accepts. Let's talk about some real-world applications of using eventual consistency. So eventual consistency is very important where high availability is critical. Systems that must remain online even during failures. So for example, going back to our previous example, let's say I have a leader and 2 followers, and a write request is replicated to these 2 followers. So in case one of the follower goes down, then one of the ways to mitigate consistency is to stop accepting writes altogether at the leader, but that comes in the cost of availability. And in most of the modern day systems, especially large scale systems, that's not acceptable. So in that case, we keep accepting writes even though we understand that the replication takes some time. So massive scale and throughput. When handling millions of reads and writes is paramount, then this eventual consistency is something we have to be content with. And acceptable stale data. When users tolerate minor delays in seeing the absolute latest information. So for example, social media feeds, seeing a post a few seconds late is generally acceptable. So of course, like consistency is paramount in very sensitive applications, for example, banking, financial transactions, etc. But for a social media feed to appear, we can see a post a few seconds later, and that's acceptable. E-commerce shopping carts. Often for non-critical parts, the exact item count might differ across different replicas. DNS propagation. Changes take time to propagate globally. IoT data analytics, sensor readings where eventual aggregation is sufficient. So what are the challenges of eventual consistency? Read your writes problem. As I mentioned before previously, users can write their data, then immediately read the stale data. And what can be the mitigation? Session stickiness, routing reads to latest writer. Then monotonic reads, reading older data after reading newer data. Mitigation, versioning, smart routing. So these are some of the advanced topics that we are going to talk about in later videos. And then conflict resolution, how to reconcile diverging versions of data, which is very important. So you will see in a later video that there can be diverging versions of data coming from the eventual consistency or asynchronous replication. So there are a few strategies to mitigate this problem. Last write wins. This is simple but can lose data. Then application specific merging, more complex but it preserves the data, where application is in charge of conflict resolution. And then version vectors or vector clocks. This is for sophisticated conflict detection. And developer complexity, of course, it requires careful thought about data consistency at the application layer. So we need to understand that eventual consistency is a core idea. It is a deliberate trade-off of immediate consistency for superior scalability and availability, and it is not a flaw. It is not a bug. It is some choice we deliberately make so that the system is highly available, even though it is not completely consistent immediately. And it requires careful design. Application logic must account for potential data staleness and conflicts. And this is a foundation for many modern large-scale distributed systems. For example, NoSQL databases like Cassandra or DynamoDB, which deal with a billion of records at a time. And then key takeaway, understand your consistency requirements and choose the model that best fits your system's needs. So this has been a quick overview of eventual consistency. There are quite a few very interesting and complex topics that are covered here, which I haven't delved much into, but we will discuss them in a later video in detail. So thanks for watching. If you like this video, please like it, share and subscribe, and I'll see you in the next one. Thank you.